I'm delighted to be here to introduce my good friend and very longtime colleague, Linda Spilker. She's been in meetings all morning, so I didn't get a chance to speak to her briefly at all about how I would introduce her today. So I had to wing it, and basically, how do we wing anything these days? We go to Google and see what we can find out. If you go search on Linda Spilker, you find she is very prominently placed. She is the Linda Spilker of the internet. Her position goes back to JPL in 1977. She was working on the Voyager project back then, so that would have been very early in the Voyager project, in fact. Before launch. Okay, so from the very beginning of Voyager and on through to the Cassini project in the present day. One of the things that really struck me about this page, the search page on Google, was the fact that you see a lot of obvious things, NASA sites and so on and so on and so forth, and science sites of various sorts. And then you get down to this one down here, IMDb. Are you familiar with the Internet Movie database? Well, Linda has an alter ego, apparently, that I didn't know about on the IMDb database. And there she is. She's actually appeared in Nova, a number of other TV programs, and so on, as herself for the most part. I did note, however, that just to make sure that we're all grateful to have her here, she's up 7% in popularity this week. But of course, she's been very involved in all research in the outer planets, but most specifically Saturn in recent years. And so her pictures that you come up with on Google are equal measure of her and a few bozos and people we don't know, and then a lot of pictures of Saturn and its ring system. Here is her homepage at JPL. Most prominently, she is a colleague of mine on the Sears team for Cassini. Sears is the pronunciation of Composite Infrared Spectrometer, CIRS. And we have been working together on that for quite a few years now, studying the thermal emission from Saturn's rings. She also has the very distinguished title of Deputy Project Scientist for the Cassini Mission, working closely with the project scientists and making sure that many, many of the details of the Cassini projects run smoothly at all times. And finally, just a personal note, as I mentioned, I've known her for a long time. At her JPL homepage, it lists selected publications, and in reverse chronological order, and going way there down to the bottom, her very first paper, I'm very pleased to see, in 1996, her name was Linda Horn back then, but the second author was some bozo named Showalter. So we've been working together a long time, and it's great to have her here. So Linda's talk will be about what Cassini has taught us about the rings of Saturn in the thermal infrared. And I'll let her go from there.
Great. Thank you, Mark.
You might want this.
Good job. Good job. Okay, well, I want to talk about the rings of Saturn as seen through infrared eyes, or as seen by Cassini Sears. And this is an overview of Saturn's rings for those of you who might not be familiar with them. They have very simple names, just the letters of the alphabet. And you can see the main rings, the A, B, and C ring. There's a Cassini division and the Encke gap. Each of these held open by tiny moons that orbit within them. There's also other rings in the Saturn system. There's the faint G ring, then the very extensive E ring, whose source we now know are the plumes coming from the south pole of Enceladus. And this is a very extensive system here for the main rings. It extends about 140,000 kilometers edge to edge. The rings are mostly made out of water ice, and they range in size from micron-sized up to tens of meters and even tiny moons that we find orbiting embedded in the rings. There's a non-icy contaminant, perhaps from micrometeoroid pollution, and we're working to try and understand that. There's a lot going on in the rings. You have aggregation and accretion in some places in the rings. Of course, you have collisions, and those tend to disrupt some of these aggregations. You have these beautiful resonances that are prominent, especially in the A ring, interactions between tiny moons that orbit just outside Saturn's rings and create these spiral density waves and bending waves inside the rings. So some key ring questions. I want to start out with what are the questions and then go into how can looking in the thermal infrared start to answer some of those questions. And first of all, the ring structure itself. Are the main rings of Saturn, the ones you can see, when you look through a telescope, are they in a multilayer or a monolayer? And the answer to that question might be yes. Maybe the largest particles are organized in a monolayer and the smaller particles perhaps in a multilayer configuration. We found with Cassini that both the A and the B rings, in other words, the bulk of the mass of the rings, comes together in some kinds of accretions, self-gravity wakes, or possibly gravitational overstabilities, viscous overstabilities. And there's lots of irregular structure that we have no idea what's controlling that structure. The ring particle properties, you want to get to things like the albedo of the individual particle, its thermal inertia, the size, shape, and spins. In other words, you want to go from the big picture of how do the rings themselves work dynamically down to the smallest particles, the ring particles, and what do they look like. I think it'd be cool if you could take a ring particle, scoop it, and bring it back to Earth and hold it in your hand. What would you see? What would it look like? Origin, age, and evolution. Those are always good questions to ask about anything in the solar system. And for the rings, why is the water ice so dominant? That's what led us in the Voyager epoch to think the rings were young. They look new and pristine. So are the rings young or are they primordial? And maybe the answer to this question might be yes also. Perhaps places in the rings, or perhaps the B ring itself, might have formed at the same time as Saturn, and perhaps some of the other rings, the C ring, perhaps the A ring, might be newer in geologic timescales. So what are some of the challenges in the infrared modeling of the rings? It's not like you can just take an individual snapshot of a ring particle, look at all of the sources of flux coming in, and you're done. No, it's not that easy, because the thermal emission is connected to the ring dynamics and the heat transport and the way the particles spin and the way they move vertically and the way they move azimuthally as they go around it. And then they go in and out of Saturn's shadow. So that is another separate, where basically you have these particles that have kind of come to some kind of thermal equilibrium and they dip into the shadow and things cool off, and you go through this cycle over and over again. If you're in the C ring, this might happen every 6 hours. You go further out in the rings, it might be 10 or 12 or even 14 hours, but you regularly go through this cycle of heating and cooling just by going through Saturn's shadow. There's many heat sources. You've got to worry about the sun, you've got the Saturn thermal and visible, and then also the interparticle heating between the particles themselves. So you have to basically follow the time history of a particle or group of particles as they go around the rings to get an idea about what temperatures you might expect. So what can we learn from infrared observations? The nice thing about having an orbiter is you can look at a wide variety of geometries. You can hang out there for a while. Cassini arrived at Saturn just 3 years after the solstice, so the sun was high in the sky, in this case shining on the southern side of the rings. We've now gone through equinox this past August where the sun was edge on, so we've had a chance to go through a season, if you will, at Saturn's rings. You can also, so solar elevation dependence, and what can this tell you about the, get an estimate of the albedo and something about the vertical structure as well. Then there's the azimuthal angle dependence, that as you go, as I said, in and out of the shadow, you can learn something about the thermal inertia, perhaps also about the wake structure in the rings. As you go around in azimuth, you actually get different filling factors because of the alignment of these structures as they change with the orientation and the orbit around the planet. You can look at also the fraction of millimeter-sized particles by how quickly the rings cool and heat up, and learn something about the smallest sizes of particles in the main rings. You have a phase angle dependence. So if you look from the Earth at Saturn's rings, you can only look through a very small phase angle range, 0 to 6 degrees. And so you get there with the spacecraft, you now have access to the full range of phase angles and both the lit and the unlit sides of the rings. And so here you can now start to get a handle on the spin state and the spin and size distribution of the particles. We've found in looking, when you can look at more than just the 0 to 6 degrees phase, there's a thermal opposition surge in phase angle. As you go to smaller phase angles, it heats up non-linearly, and that was a very interesting result. And this can give you some indication of the volume filling factor of the rings and perhaps the surface roughness and something about the particle shapes. They're probably not nice, idealized little snowballs or little, billiard ball ice particles. There are probably some irregular shapes, and certainly the clumping together produces an irregular shape. And then finally, something you can't do from the Earth very well or very often is to get the unlit side temperatures. And that tells you a great deal about the vertical structure and the vertical motion. Do the ring particles, twice in orbit go from the top to the bottom side of the rings? How does that ring structure work? And I've just listed some papers here that address these issues. Well, here's the instrument that we use to look at the rings. It's the Composite Infrared Spectrometer. It's actually based on the Voyager IRIS instrument that flew by Jupiter, Saturn on out to Uranus and Neptune, with just, of course, improvements that come along with just launching, 20 years later. It's a Fourier transform spectrometer. We have a series of focal planes 4, 3, and 1. You'll notice 2 is missing. It was de-scoped at some point early before launch, so then we had to sort of stretch the range so we could cover from essentially 7 microns out to 1 millimeter. We can also program the spectral resolution, looking at half wave number. It's very good to get composition, but it takes a long time to collect, like 45 seconds to collect a single spectrum. If you just want temperature and you want to map the Planck function, then you go to much shorter scan times, which is much lower resolution. So that'd be 15 wave numbers. You can do that in about 3 seconds. So we can sort of program then the range of resolution depending on what you're looking for with your observations. The ring temperatures range, we know now, from about 45 Kelvin up to 120 Kelvin. The maximum emission is around 50 microns or 200 wave numbers if you're a wave number fan. The sizes of the field of view, we have a circular 3.9 milliradian field of view. That's our workhorse field of view. It goes over that peak in the Planck spectrum. And then we have 2 arrays, FP3 and 4 are 1 by 10 arrays, much higher spatial resolution, 0.3 milliradians, excuse me. And also with these, they have to be cooled, so they have a separate cooler. They need to be kept at a lower temperature than the instrument temperature to have higher signal to noise. So our workhorse is focal plane 1, so most of the information I'll share with you today comes from focal plane 1. Here's an example of how we do a Sears ring observation. Here's that circular field of view. You'll notice it's distorted. Often we're looking at the rings where they're not flat on like a bullseye, but they're closed a little bit. If you map that then into the rings looking straight down, you get sort of an elliptical or oblong field of view. What we're seeing within an individual field of view, if this is a ring particle, it's color-coded here for temperature. Here's the warmest temperature in the south of the particle, going on up to the colder temperatures. And if you divide up that ring particle into individual facets, each facet is going to have a slightly different temperature depending on the sources of energy that it receives from the sun, Saturn, and so on. So it really depends on what side of the ring particle you're looking at on what temperature you might measure. So the first takeaway message is when you're looking at a ring particle, you're really seeing a range of temperatures across that particle. And if you look toward the day side of the particle, here's an example of some Sears data. This is what you might see. Here's 100 Kelvin, 50 Kelvin, just for comparison. But this is really an average of a large number of temperatures across. If you look at the night side or higher phase angles, you're going to get a colder temperature for the same ring particle. Basically, what we measure the intensity is the Planck function times the emissivity. This is the filling factor, and you basically want to look at each little facet across the side of the particle that you see, and ratio to the temperatures of those facets, and you end up with some average temperature of the particle. You could sort of think it's close to a physical temperature. And that's what you would actually measure with Sears. And the advantage here is that you get a complete spectrum. You can fit it. We tend to fit from about 100 to 400 wave numbers. The temperature tends to be constant in that range. As you go to longer and longer wavelengths, we know that the particles become more and more transparent. The temperatures get lower and lower. So we tend to try and fit in the range where we expect a constant temperature. Just some examples of geometries. This shows the phase angle, spacecraft elevation, the distance from Saturn and Saturn radii, and the solar elevation from 2004 in June when we arrived, July 1st, through 2009. What you notice here is you can see we went through a whole range of phase angles, which is great. There are some blank spots there. It just means that some people like to get the rings out of the way. Who would want to do that? So we have some orbits that are equatorial, and that's when the atmospheric people are very happy because they can see all of Saturn without anything in the way. So the blank regions are where we didn't take data because we were in the equatorial plane. And you can see that the solar elevation is slowly decreasing as we head through the mission. Another way to look at this here is these are the orbits for Cassini. All of these white dashed lines represent the orbits over the prime mission and into the first year of the equinox mission. And then all of these little color codings indicate red is the high solar elevations on down to the low solar elevations. This view, you're looking top down on Saturn. The sun is off to your left. This view here shows you the richness in going out of plane. Now this is the equatorial plane, and these are the orbits and how we covered the system looking out of plane. And you can just sort of take away the orbits, and this is the data sets that you're left with. The orbits kind of help your eye know what you're looking at. Okay, for Sears data analysis, I want to talk about the ring particle temperature. Look at what we've learned so far about the temperature as a function of optical depth, phase angle, and solar elevation. Give you a look into some of our very preliminary results from the equinox data. Those are the coldest temperatures we've observed to date, and we got a nice mapping of both the lit and the unlit sides of the rings at equinox. I'd like to then share with you a Sears ring movie and then finish up with a little bit of what's in the future for ring science and for Cassini. This shows the general behavior outside the shadow, and our initial goal coming into the mission was to get a multidimensional map of the rings in the infrared and provide the key parameters that you need for modeling. So what's shown here is here's the temperature of the rings as a function of optical depth. Here's the C ring and Cassini division, the A ring and the B ring. And what you notice is that the minimum temperatures are in the unlit side of the B ring. The maximum range of temperatures are in the C ring. In particular, you have a large thermal source with Saturn, and that really helps with the input there. The low temperature, the temperature tends to decrease as you increase the optical depth on the unlit side. That's no surprise. You're just blocking more and more of the sunlight, so you have less energy to be transmitted to heat up that side of the rings. And the key here is to try and understand the vertical structure and the vertical motion of the ring particles, and I'll talk in more detail about some of the modeling we've been doing. This is the general behavior outside the shadow, plotting a little bit different. This is the phase angle now as a function of radial distance from the planet. You can see the C ring, B ring, Cassini division, and A ring. And this is for the lit side of the rings, and this is for the unlit side of the rings. And to first order, what we found out is that the temperature depends primarily on phase angle. As you basically go from essentially seeing what would look like a full moon or a fully illuminated particle to high phase angles where you see basically the dark sides, the temperatures tend to fall off with increasing phase angle. And you can see here's the C ring. Red is warm, and then blue is colder, and you can see things cooling off. B ring, the same thing on the lit side of the rings. And for some people, this was a surprise because we didn't know if the ring particles at Saturn were rotating rapidly enough to be isothermal. And so there were some expectations that we might find, perhaps, at least for some ring regions, isothermal rings, and the temperatures would be constant. And this, of course, is a much more interesting story because what it's telling you is you need some kind of a slow rotator, slowly enough rotating to give you that difference in temperature with phase angle. On the unlit side of the rings, notice that for the optically thickest piece of the B ring, really for the entire B ring, it doesn't matter what your phase angle is. It's the same temperature equally. In other words, it doesn't seem to know day or night as relative to the sun on the unlit side of the rings. Whereas the Cassini division, you do see a change with increasing phase angle. Same thing, C ring, Cassini division. A ring is a little bit of a change, but not as much. So clearly the amount of particles, the density of particles makes a difference in shadowing on the unlit side. So how do we start about constraining the particle properties? Well, what's shown here is very early on we had a set of orbits where it allowed us to get 4 different geometries. And it's illustrated here if this is the planet plus the rings, and this is the sun shining down. We could look at lit low phase and lit high phase, although this is the south side of the rings now, the unlit high and the unlit low phase. And here we've just painted those temperatures on the rings. You can see going from low phase to high phase, you can see the cooling across the rings. And on the unlit side, you can see very easily that the B ring really isn't changing temperature as the C ring is cooling with phase angle. In fact, the C ring is so optically thin that it really doesn't know, it doesn't matter if you look on what we call the lit or the unlit side, you see the same temperature. The particles are far enough apart that you don't really have a shadowing or an unlit effect for the C ring and for the Cassini division. Turning those pretty pictures into plots here, what I'm showing is the same data now. This is for the lit side of the rings, and this is the unlit rings, showing the temperature as a function of distance from the planet. The dashed lines indicate the boundaries of each of the rings. And what's overplotted here is the PPS optical depth. When we put together this set of observations, all we had were the Voyager photopolarimeter single stellar occultation that we had of the rings of Saturn. And so we put that together and noticed that some of the features follow optical depth. So there's a positive correlation here in the B ring with the optical depth change and the temperature change, and an anti-correlation on the unlit side. What's interesting to note is phase angle makes a difference in another respect. When you're at low phase angles, you can see a lot more structure within the ring itself, especially within the C ring. And as you go to higher phase and less illuminated particle, this washes out. You can see the effect of this washing out. And in fact, the temperatures seem to almost start to, across at least the A and the B rings further from the planet, become, very much equivalent at much higher phase angles. You can see very clearly here in the B ring that, it doesn't matter what the phase angle is, you're getting essentially the same temperature. Okay, let's move on to talking a little bit about modeling now that we have the data in hand. And so, as I mentioned, the rings are probably a mixture of monolayer for the large particles and a multilayer for the small particles. And so this makes precise modeling difficult. And if you throw in the clumping and the wakes on top of it, that's just another complication that you have to include in your models. So pretty much what we've done to date is just consider individual particles, looking at some simple models with just two sizes or maybe even a distribution of sizes. For the multilayer models, tends to be just calculations of classical radiative transfer following the particles until they even out in temperature. No volume filling factor assumed. The monolayer approximation, you include the volume filling factor, but you use just a very simple analytic form for the shadowing function of the particles, or a semi-analytic form. And so when you try and extend then to this cloud of smaller particles, it makes it much more difficult because the monolayer is literally considering a single layer of equally sized particles. So that but you can learn something by applying these models. For the multilayer approximation, what you assume is plane parallel approximation, no wakes included in this. You've got the sun as a source, Saturn visible and thermal, and the interparticle heating between the particles themselves. You assume a heterogeneous vertical spin distribution, and also two sizes of particles. Here are the non-spinning Lambertians and these isothermal small particles. Assume a factor of 3 difference in how much they go back and forth across the ring plane. And in the B ring, we found that it works a little bit better to assume a bouncing case. The B ring is so thick, we assume that the particle really can't very easily go from one side of the rings to another. So we assume that the particles bounce at the midplane, and look at both the bouncing case and the case, standard case. And then you also include the azimuthal motion and include the shadow effects and all of this into your model, and you run it until it reaches an equilibrium state. Okay, taking those 4 curves that I showed you earlier, you can now run this model by looking at what's the fraction of fast rotators that you might find. This is so the fraction of fast rotators, the isothermal particles, assuming the other fraction are the slowly spinning Lambertian particles. And you look at how the temperature changes with the fraction of fast rotators. And each of these curves here, color-coded, go back to those plots I showed you earlier. And it's just picking a place in the C ring, in the B ring, and in the A ring, the inner A ring, and the outer A ring, and trying to find the best fits to the data. You can do a pretty good job in the C ring. It's not very optically thick. It's a nice test of the classical radiative transfer. The B ring, it's a little bit more problematic when you get to the unlit side of the rings, even with this bouncing assumption. And then the A ring, also problematic at the unlit side. But again, In the case of the B ring and the A ring, the classical assumption is really not very good because the particles are clumping together, forming self-gravity wakes or also wakes in the B ring. So this is where the classical model tends to break down a bit. But you can still learn something from it. Then you can take this fraction of fast rotators that you found over here, and you can try and find an albedo, a fitted albedo, if you will, by looking at where the intersections occur from the number of fraction of fast rotators here, and then can just compare it to other data sets. These dashed lines are the Porco et al. 2005. There's some points here from the Lerat paper and so on, and just get sort of a fitted albedo in this case by looking at just these 4 curves. You can also do something with the thermal inertias, again with the same assumption that you know the fraction of fast rotators, these blue boxes, correspond to the range over which we saw those. You can see for the case of the A ring, the inner and outer A ring, you have a large range of thermal inertia. But the takeaway message here is if you look at the values of thermal inertia, they're quite small. The case of the C ring, it might be on the order of maybe 5 or 5 to 10, something like that. You know, maybe you get up to, you know, maybe 20 or so. But the thermal inertia is very, very small. It's like 4 orders of magnitude less than you would have for solid water ice. In fact, it's even smaller than what we've seen with some of the Saturnian satellites. So what that indicates is you probably have very fluffy particles. You have a lot of space in between that you can have this fluffiness and very low thermal inertia. So you could change temperature very quickly. You go into the shadow, the temperature very quickly goes down and reaches an equilibrium. Going back to the temperature versus phase angle, I talked about the fact that there appears to be this thermal surge in temperature. These are all plots of temperature versus phase angle now. Starting with the C ring, inner and outer B ring, Cassini division, and inner and outer A ring, and this little bar is about 30 degrees, just indicating that it's very broad compared to what you would expect if you looked in the visible for the coherent backscatter where that surge is in just the last degree or so. This is very broad. And it could be a function of shadowing. It looks like the surge is most prominent in the optically thickest rings. But it could also have something to do with the intrinsic characteristics of the particles themselves. What the surfaces of the particles look like, we know they're probably fluffy. Maybe they have some kind of contouring. Imagine a ring particle now kind of like an asteroid. And maybe if you use similar kinds of modeling, you can explain this broad, very broad thermal surge. In looking at the phase angle dependence, took a look at this multi-layer model with classical radiative transfer. This just shows for several solar elevations what we found for the B ring and the C ring. And if you run the multi-layer model calculations, what you find is you can't really reproduce this opposition surge that you see in the data. So you need to add some other kind of an effect, volumetric effect or an intrinsic effect, to be able to explain this surge. So it just doesn't fall out naturally from the modeling. Moving on to the changes with solar elevation, this shows a series of curves. Red is the highest solar elevation. You can see the temperatures decreasing across all of the rings as the solar elevation decreases. And you can also see that the structure that we see in the B ring in particular is a good example, that starts to wash out as you go to lower and lower solar elevations. These are some curves now picking a single location in each of the A, B, and C rings to look at the trends. We've characterized these by looking at the lit side at low and high phase angle. This is low, this is high, and also looking at the unlit side at low phase angle and trying to use one of these semi-analytic shadowing functions to model the behavior of the rings. And so now we have a complete data set, and again, it's not as straightforward. This is using a monolayer approximation, not straightforward to get a good match to the data. Just a little bit about the equinox observations. What we tend to do around equinox is to take a series of radial scans. These red little caterpillars here, those are the individual Sears fields of view overplotted. And this is looking at the south side of the rings. Phase angle was very high. You can notice that the shadow is coming out almost toward you, so you're seeing mostly the night side of the particles. Then here, the north side, what we did is we looked at noon and at midnight to see if we could see any difference as the particles go in and out of the shadow. And basically, you're running the experiment of turning the sun off. And what do you see at equinox when you turn off the sun. Here's some of those data. This is for the south side of the rings, a couple of different local times. The north side of the rings, and what we're seeing here is that the midnight local time and the noon local time are essentially the same temperature. In other words, the assumption that you essentially turned off the sun is a good assumption, and you've reached a really stable thermal equilibrium. You know, equinox takes about 4 days at Saturn. The sun is not a point source. That's how long it takes for the sun to transit completely from one side of the rings to the other. We just did some simple calculations and said, okay, if you just look at the thermal heating coming from Saturn, the red line is if you assume the heating comes from both hemispheres of Saturn. That's a good approximation for the C ring and the Cassini division here. Because they're optically thin enough, you get input from both sides of Saturn. But in the case of the blue line, with just one hemisphere of heating, that's more appropriate here for the B ring. What's interesting is the A ring seems to, with the wakes in it, seems to be more in the heating from both sides of Saturn in this particular model when comparing to our data. So that was an interesting result, whereas the B ring is much more like heating from a single hemisphere. You'll notice there's sort of a rollover here, and that's when you get so close to Saturn in the C ring that you're no longer seeing the whole disk, you're only seeing a part of the disk of Saturn. And that's what causes that rollover effect. Another thing we looked for, really neat pictures. You know, if you go online to the Cassini website, at equinox, it's a great time to look for any warps or anything in the rings that would be sticking up above those few meters of ring thickness. And those appear then bright in the sunlight. And in particular, what's bright here is you can see, just barely make out, there's some ringlets in the Encke division where Pan is orbiting. Clearly, those are vertically extended. You can see places where they appear discontinuous. Sometimes they're above the ring, and you see on the other side they're below, and so they'd be bright on the other side. You can see some of these structures here I've indicated with the blue lines. They're bending waves. Mimas is slightly inclined and actually causes particles to lift up above and below the ring plane. And equinox is really a neat time to look for those, because now you can get a sense of how high above the ring plane they go. This is the Mimas 5 to 3. It's bright in the images, and it casts a shadow. And so knowing what the angle of the sun is and the length of the shadow, you can get the height of the bending wave. And when we use it in the thermal is to look for these particles sticking up above should be much warmer than the background material. And could we see that in our highest resolution look at the Sears data? And here the blue lines indicate the locations of the bending waves. Here's a density wave. There's a slight hint that maybe we see a thermal effect, and we're working to further reduce the data. And in fact, we did a calculation to say, if you assume that the ring is some background temperature, and you assume different temperatures for this piece of bending wave, what temperature would you expect to see based on the fraction of the cross section? Our footprint is pretty big. You know, it's like, 2,000 or 3,000 kilometers across, and if you only fill it by 1 or 2% with something much warmer, it's a T to the 4th effect. What temperature would you expect to see versus, say, a background of 43 Kelvin? If it heats up to 90 Kelvin and it's a little over 1%, you might see a few degrees increase up to maybe 49 or something. So that's the order of magnitude kind of effect that we might see with the bending waves. It turns out the density waves also are bright, and so it appears that in that first wavelength of the density waves, the particles are squeezed together. Mark had a really great image showing what happens if you put sort of particles in a box and squeeze them. They have no place to go but up. And so those first wavelengths of the density waves where the particles are tightly packed are bright also. And if you look, in fact, I can go back and you can get a sense of that. If you see these bright linear, these features that go all the way around, those are the first wavelengths of a lot of the density waves. So that was a neat result too. Okay, back to the monolayer model. In this case at equinox, what's nice is you can basically take out the sun as a source. And so that makes your problem much simpler. So same model, but now you just take out one of your sources of energy. And so we can do some modeling in this case, again using the multi-layer model. You can look now at the temperature you'd expect to see. The 3 different curves assume all fast rotators, all slow rotators is the red curve. The green curve is if you have a 50-50 mix of each of those. And now this is plotted as a function of local hour angle around the ring. You can see in the case of the B ring and the A ring, basically you wouldn't expect to see any change with ring local time. And in the case of the C ring, you might be able to distinguish between a large population of either fast rotators or slow rotators if you look at different local times across the ring. But of course, if it's close to 50-50, then it too seems to would even out in temperature. So again, running this model, the sun turned off. What we find is that you get basically good fits for the B ring here and the C ring and the Cassini division. I've put green arrows in here because these little diamonds that you can barely see are the fits overplotted on the data at two different local times, midnight and 10 hours local time. In the case of the A ring, the model is colder than what you expect to see in the A ring. And this might be a wake effect, but it's significant, quite a few degrees colder in the model than we actually see in the data. So we're working to see how the wakes could be causing this. In the A ring, the wakes clump together and form these structures, but those structures are ephemeral. They kind of come together and come apart. And what we found from stellar occultation data is the spaces in between the wakes are much larger than the widths of the wakes themselves. So maybe that allows energy to get in other ways. I showed you the example of maybe heating from both hemispheres of Saturn, for example, with the wakes. And that just shows the A ring where it's not agreeing. Looking at the monolayer model, in this case, showing again the data, and then these symbols are the model plots. In this case, the B ring comes out too warm in the model, and it does a better job fitting the A ring. When you look at the monolayer assumption, all particles the same size, just spread out evenly in a flat layer. And that's the one point that's not in the B ring point, this case, not in agreement. So some of the conclusions: the ring particle temperatures decrease with decreasing phase angle and solar elevation, and the temperatures decrease with increasing optical depth as well. At equinox, the main heating source appears to be the Saturn visible and thermal, makes the experiment much simpler. You take away that solar source. To first order, the rings cool with increasing distance from Saturn. I just give a range of temperatures that we see as the rings cool. There's a hint of the -5 to 3 bending wave in the thermal data. The piece that we're looking at now is if you see a higher temperature in the bending wave region, then it should cool off when you go in the shadow. And that's the piece we're trying to put together next. The north and south side temperature differences through equinox, any of the differences we see are probably phase angle driven, although it doesn't look like we really see any differences. The model fits for the multilayer model are within errors for the B and C rings. The A ring, it might be the wakes that's causing the difference. And our goal, of course, is with the thermal, you want to understand the ring as a whole, but to understand the individual ring particle properties. And with equinox, in particular, this gives us a chance to get a handle on some of these properties. We put together a little movie. We posted this on the Cassini webpage. I just want to show you the movie. It shows the rings both for the lit and the unlit sides, and you can visually see how the temperatures change, where in this case, red is warm. And as you go toward the blue and the purple, the rings are colder. Okay, looks like I gotta. It's only halfway. I can't grab anything at the top. Technical difficulties.
Okay.
It's stuck.
Here we go. There. It's a remarkable eye-hand combination,
Yeah.
which I don't normally have.
Great,
There.
thanks.
There.
Okay, what you're going to see is that the behavior of the rings, we've gone all the way back to the start of the mission, looking at the ring temperatures when the sun is about 23 degrees ahead. This just shows Saturn, the fact that we get a unique view having an orbiter in place. Put Saturn together. This just shows, you can see the icon up here. This is the decreasing solar elevation, and you can watch the rings. The maximum and minimum temperatures are shown here. Watch as they cool as you get close to equinox, and there's really dramatic cooling, especially on the lit side, in the last few degrees before equinox. Then if you look at the unlit side of the rings, the side that you don't see from the Earth, again, starting out, you notice that the core of the B ring is pretty cold. It's blue to start out with, in the low 70s, and you can see that the temperature cools, the core just sort of spreads, and then all of a sudden, as you get lower and lower, it just spreads across the B ring and the A ring, and then finally moving in, cooling off the C ring and Cassini division as well, getting essentially the same temperatures on the lit and the unlit sides of the rings. Okay, going back, I just have a few more. So where do we go from here in looking at the modeling? We've got the multi-layer modeling with classical radiative transfer, the monolayer. The next step is to go into ray tracing. And that involves running dynamical simulations to get the distribution of particles and then use ray tracing to predict what the temperatures might be. Here's sort of a classical multi-layer. If you put wakes into it, you'll notice that you get these structures that form in the rings. Now I want to say a little bit about, okay, we have these data now through equinox. Where's Cassini headed? And in particular, what can we do with the rings? Well, Cassini has a proposed 7-year extension. That extension would start hopefully in next October. We're not funded yet, so we've asked NASA for money for this mission. What we'd like to do is go through another season at Saturn, basically through equinox up to solstice. And this allows us to look at a variety of things, not only for the rings, but for Titan, for Enceladus, for the planet itself, to look for seasonal changes. And we still continue to make new discoveries across the disciplines with Cassini. So the Solstice Tour would start next October. It would be 7 years long. The proposed tour has 160 orbits, including 56 Titan flybys, 12 Enceladus flybys, and 5 targeted flybys of other icy satellites. So in fact, we're already starting to discuss how do you divvy up 160 orbit pie, amongst all of these different disciplines. What's really exciting to me is how we end the mission with Cassini. We have planetary quarantine requirements, and so we have to find a way that we don't impact inadvertently either Enceladus or Titan. And so what we're proposing to do is to hop into the space between the innermost edge of the D ring and the planet and have a series of short period orbits in there that would last not quite a year. There'd be 20 orbits that would have periapses in very close to the F ring. That's just outside the main rings. Then we'd hop in and get 22 orbits between the D ring and Saturn's atmosphere. And what we're carefully studying now with our data is to make sure that that region is really clear. But what we're going to do with Cassini is if we happen to run into something that's bigger than we expected and the spacecraft is no longer functioning, it would naturally by itself just walk into Saturn and burn up in Saturn's atmosphere. We have a critical inclination of 63 degrees, and this allows it so the periapse doesn't precess or doesn't move about, and we stay with the same periapse in at the equatorial plane at Saturn. And the current impact date is September 15th, 2017. Job security. This just shows a profile. Here's our prime mission. This is the green. Here's the equinox mission, the 2 years that we're in at the current time, and the proposed XXM, or what we're calling Solstice mission. You can see here, this is a plot of time and looking at the declination. The red line is for the sun, and the blue curve shows the declination of the Earth as a function of time. And this view just shows what Saturn looks like. You're basically going from south side of the rings illuminated all the way to the rings fully open in the northern hemisphere. And we didn't get a chance to really look at the rings at the highest solar elevation. So that would be a very interesting thing to last until the solstice. We think the spacecraft has enough fuel and is healthy enough to go that amount of time. This is an overview of all of the Cassini mission. If you want it in one slide, what it looks like, this shows the prime mission here, equinox and solstice. It shows you the years of the tour. You would like, a 13-year mission. That would be great. Number of orbits per year, number of Titan flybys. You just count them up. Here's the Huygens probe falling into the atmosphere of Titan. Number of Enceladus flybys. You can see after we discovered the plumes, all of a sudden we were very interested in really boosting up the number of these flybys and in flying the spacecraft directly through the plume. Other icy satellites here, and this just shows again the view of Saturn as seen from the sun. So some key objectives just quickly. The Saturn internal structure. Once you hop in that close to the planet, we think you can maybe get Saturn's gravity field up to J10. That would really help us understand perhaps the structure of the core and how the interior of Saturn is organized. We think we can get the magnetic field up to degree 6. For those of you who followed the Cassini Mission, we know that the spin axis and the magnetic field axis are almost perfectly co-aligned, and it's wreaking havoc in trying to get something as simple as what's the length of a day? How long does it take for the interior of Saturn to rotate once? We don't know the answer to that question, and we hope to get that answer by jumping into this orbit to get the internal rotation rate for the planet. The ring mass, that's very important if you want to address the questions of the ring age. Once you hop into that orbit, the ring mass is now outside, and you stand a chance of measuring, in particular, the mass of the B ring. The B ring is something we haven't been able to penetrate with stellar occultations or radio occultations, so its true optical depth is really not known for the thickest part of the B ring. So the hope, if the mass of the B ring goes up by a factor of 10, there could be enough material to have survived since the time Saturn formed. So a very interesting question with the ring mass. We want to study the ionosphere, the innermost radiation belts, and the D ring. Look at the in situ plasma and the aurora. This is a wonderful place to do that. Cassini discovered an inner radiation belt in this region between the innermost D ring and the planet. And so we get some in situ measurements with the fields and particles instruments. Highest resolution studies of the rings. When you come roaring down in that space, you can look off to the side and you're going to get incredibly, exquisitely high resolution on the rings. Some places higher than we had for the Saturn orbit insertion, which is our highest resolution on the rings. And then the atmospheric studies as well. And if you think about it, this mission we're proposing for the end of Cassini is very much like the Juno mission at Jupiter. So now you'd have very similar studies going on, and just coincidentally, Juno will be doing its prime mission at Jupiter at about the same time Cassini will be doing this at Saturn. So just coincidence in how they lined up. So basically getting a new frontiers class of mission with the end of mission scenario for Cassini. I just want to end with a couple of little movies. If you could ride on the spacecraft and ride through one of these orbits, here's what you would see. So now you're on Cassini, you're going to go plunging in between the D ring and the atmosphere. There you go, and on out, and you can see the sun. And so we'd have 22 of these orbits to make studies, and it takes only a matter of an hour, a little over an hour, to go from basically the North Pole through the South Pole. So you go very quickly through that range of geometries. Here's another slightly different way. The blue orbits are just outside the F ring. The gold orbits here are the ones that would be between the planet and the rings. So that just gives you a sense of the geometry. We set it up so that when you're closer to the planet, you're behind the planet, and you can do the gravity measurements you need to do, and even get some very interesting and high-resolution ring occultations with the radio science system. And so I will just end with that. In fact, I might just go back and show, let's see, I have to go back one more. Maybe to show this movie one more time. It's really cool. So this will be Cassini, and like I say, if something happens to the spacecraft, we'll just naturally walk into and burn up in the atmosphere of Saturn. And if we have extra delta V, we'll use it so we can sort of back away and take even a little bit longer in this series of very, very interesting orbits. Thank you very much. I'd be happy to take any questions.
Before we get to the questions, there is a tradition here at SETI that our speakers receive a lovely commemorative pin from the SETI Institute. So,
why, thank you. Does this work to get me in the door? And
yes, it's a security pin as well. But, yes, we'd be happy to take any questions you have. Jack?
You mentioned at the beginning there was a possibility that you might be able to see some heating from internal processes, collisions. Is that quantitatively reasonable with the equinox data?
Yeah, I don't think we would see. I think the collisions are gentle enough. If I said that, that's not correct. You wouldn't see heating from collisions of particles, no.
It seemed like it would be an unlikely thing, but it wasn't.
Too gentle, no. Maybe something, if a meteor hit, and you might see something there, but yeah.
Hi, I really enjoyed your talk. I was wondering, at the beginning you mentioned the composition of the ring material, and I wondered with Sears if you can distinguish between the hydrogen isotopes, that if you could, it might give insight into the origin of the ring material.
That's a good question. Could we determine the difference with the hydrogen isotopes in the rings? We haven't looked at that in detail. We're looking basically now at amorphous versus crystalline ice and that sort of thing. I think in an atmosphere it's a little easier to do that hydrogen to helium ratio and the hydrogen isotopes because you have a gaseous medium, and I'm not sure you could do anything similar with a solid like the ring particles.
Linda, did you showed that thermal opposition effect that went out to about 30 degrees. What ring was that for, and do you see the same opposition effect across all rings, or do you see it varying, or is that something that you still looking to get complete data on? I can understand that it might be tough to get those observations, but
yeah, the question was, what do we see with the thermal opposition surge in that first 30 degrees of phase angle? And we primarily see that in the B ring and the A ring, where the rings are optically thick enough that you could possibly have mutual shadowing going on as a possible effect. There's hints of it in the C ring and Cassini division, but they have very different shapes to their phase curves. What we'd like to do is get phase curves at several different solar elevations and watch and see, because basically you're changing the length of the shadow as you look at different solar elevations and see, does that change what you see if it's shadow driven for the opposition surge, or is it more intrinsic to the particles or the clumping themselves?
This is a man on the street type question, but in addition to what you've learned about the rings, has studying the rings taught us anything about anything other than the rings? Has there been any spillover and observations?
Great question. Why study rings, and does it have any spillover into other areas? Well, I talked about these spiral density waves. They're a really nice analogy to spiral galaxies. A lot of the same physics is at work there. These wakes and clumping together are very interesting in regards to what might happen with perhaps planetary formation in a planetary disk. You can almost think of like the Saturn system as a miniature solar system, and so how these processes occur around the planet might tell you something about how the solar system itself possibly evolves. So we do look at other possible applications, and that's a good question.
Any more questions?
So what is the state of the spacecraft right now if you had to grade it on a health scale, 0 to 10?
Okay, what's the state of the spacecraft, especially if we had to grade it on a scale? Well, it turns out that the majority of the systems on the spacecraft are redundant. We have like 2 of the major computers, we have 2 main engines, 2 sets of thrusters, and so on. And so we have had to go to backup systems in very few cases. One of those were the reaction wheels. We need 3 reaction wheels to turn the spacecraft. We had a 4th as a backup. We have gone to the 4th reaction wheel, and now we're carefully monitoring the health of the other reaction wheels. It's a moving part, it has bearings, it has lubricant, and so we have to do some careful things to maintain and extend the life of these reaction wheels. Very recently we had to switch to some backup thrusters, the backup set of thrusters. And so you can see, we're about halfway through the main mission that we're interested in, and we've gone to the backup thrusters, and now we're more careful in how we use those to more evenly use those. It turns out we used one direction, the Z thrusters, more than the other thrusters, and so we're trying to balance the usage a little bit better. But overall, the electronics on the spacecraft are healthy. We still have 2 viable main engines. All of the things seem to be working. We had little failures here and there with the instruments, bits and pieces. Some of the articulating parts aren't articulating as well, or perhaps not at all. And so moving parts are the things that tend to wear out, I think, first. But overall, I'd give it an A.
So I was wondering if, do all the rings rotate in the same direction, and is that the same as the rotation of the planet?
Yeah, do all the rings rotate in the same direction, and is that the same direction as the planet and the moons? The answer is yes. If you think of this big cloud from which Saturn formed, condensing in and having, a certain spin associated with it, everybody is what we call prograde direction. To find something retrograde, if you go far enough out in the Saturn system to the captured objects, like Phoebe, then you will find objects that may be retrograde or have different inclinations. But the rings, the moons, and the planet all rotate in the same direction.
You made mention earlier about some occultation measurements, and I thought you said something about radio. Are you actually using the radio signal back to Earth? To make
Yes, we do.
measurements?
Yeah. Do we use the radio signal for occultations? We have X, S, and Ka bands, so we have 3 frequencies we can use. We have set up certain orbits of the mission so that the Earth crosses diametrically through the rings, and we can actually send a radio signal through the rings and look at the attenuation and the phase changes, get information about the size of the particles and other very interesting features by using the radio wavelengths. We also use stellar occultations in the near infrared and the ultraviolet to probe the rings too.
You could give me an intuitive feel for how this ring system can precess as the poles of Saturn precess under the, I guess, the sun's influence. And,
Okay.
You know, I understand they're only a few meters thick, and yet the whole thing precesses as a body, I guess, over 100,000 plus years.
Yeah, well, there's 2 kinds of, first of all, the rings pretty much stay in the equatorial plane of Saturn. And that's really driven by the fact that Saturn is oblate. It has what they call a large J2 term, sort of like a squash-looking planet. And that oblateness really, and if a ring particle tries to go too much out of plane over a long time, unless there's a energy supplied to it, like bending waves or something like that, you tend to just keep all those particles very neatly confined in that plane. So I don't know if Saturn's pole moves over 100,000 years, you know, if the Saturn's equatorial plane changes, then the rings, of course, would follow suit.
Any more questions? Okay, well, let's thank our speaker once again. Thanks, Linda.
Thank you. Okay.